Hello, everyone. Welcome to CMP210, Modernize Apple Platform Development with AWS and EC2 Mac. I'm Manish Rathore. I'm a Senior Manager of Product Management here in Amazon EC2. I was the product manager 4 years back who launched EC2 Mac. And I have with me Tim Sutton, who is a Senior Mac Mini Rebooter at Block. Super excited to have him here to talk about his journey of adopting EC2 Mac. So to just get the ball rolling, 6 years ago, we started looking into bringing Apple to the cloud with EC2 Mac instances. And the use case that we wanted to address at that time when we were talking to the customers was we had lots and lots of customers who had migrated all their workloads to the cloud. They were benefiting from all the AWS services that existed out there, but they had this last leftover workloads that they couldn't move to the cloud, which was the iOS and macOS build platform for their Apple applications. You had customers who had Macs sitting in a desk, in a closet, or in a data center, and to be honest, when we started talking to the customers, it was super painful and super hard to manage that Mac infrastructure. So customers came to us and asked, hey, can we move these workloads to the cloud? And because to be able to build applications for the Apple platforms, you need tooling like Xcode. Xcode could only run on macOS. macOS could only run on Apple-branded hardware. So in order to be able to help these customers move those workloads to the cloud, we had to bring Apple to AWS data centers. So quite a few serendipitous things happened. First thing, we had Apple launch the 2018 Intel Mac Mini, which had a much better performance, much better connectivity, and more importantly, around a year and a half back, we had introduced this new thing called AWS Nitro System, which is a set of building blocks that enables us to take a server like a Mac from an Apple, same Mac that you would probably buy on a retail website or walk into a store, get it, integrate it with the entire control plane and the data plane and make it available to the customers as EC2 instance. So long story short, we launched with x86 Macs exactly 4 years ago at this conference in 2020. And since then, we have continued to expand the ecosystem and support, not just in terms of the Macs we support on AWS, but also support for different AWS services so that you can continue modernizing your iOS and macOS build infrastructure. So fast forward 4 years, and in a funny way, it's a short time. It's been a long time, as well as it only feels like yesterday. We have added support for Apple Silicon Macs. We have the broadest selection of Apple Silicon Macs anywhere in the cloud now, with the M1, with the M2s, with the M2 Pros, with the Mac Studios, and the support for M4 and M4 Pro coming soon. And over the years, as Apple has innovated on their silicon to improve the CPU performance and the memory bandwidth, as well as the IOPS, we have been able to bring all those innovations to you directly. So compared to x86 Mac instances, like customers have reported up to 4 times better build performance and 60% better price performance than they were getting previously on their x86 instances. And finally, the best thing that we like about EC2 Mac instances is how cloud-like experience we can give to our customers. So compared to like putting in purchase orders and working through your procurement team, waiting weeks to get Mac, you can just provision your macOS environments in minutes, pay for actually what you're doing or what you're using, and integrate with dozens of AWS services, be it auto-scaling, be it virtual private cloud, and so on. And that just makes the whole iOS CI/CD experience so much more better where you are not spending time securing your infrastructure or making it more efficient or improving the performance of your build pipelines. So over the last 4 years, it has been amazing to see how customers have ended up adopting EC2 Mac. And today we have tens of thousands of customers who are running their Apple build pipelines on EC2 Mac instances. We have had customers like Pinterest, Goldman Sachs, and Riot who have reported up to 4 times better build performance, 3 times higher parallel builds, and up to 80% reduction in build failures by moving their on-prem macOS build infrastructure to AWS. And one of the things that I personally enjoy a lot is hearing about the customer migrating their workloads from on-premises to the cloud, what their experience was, what their learning was. And a lot of times we learn a lot from how our customers go through that journey. So without much ado, I would like to invite Tim Sutton to talk about his journey right from the evaluation to productionizing EC2 Mac. What were his learnings? What were the key takeaways? And what are the things that he experienced firsthand that he can share with you so that you can keep those in mind as in when you're going through this modernization journey? Over to you, Tim.
Thanks a lot, Manish. Thanks everyone for making it out to one of the last sessions, last day of the conference. So appreciate your time and attention for making it out here. My name's Tim Sutton. Senior Mac Mini Rebooter is not my official title. That's the joke title that I tell people at parties. I'll tell today the story of how we migrated from a self-hosted Mac continuous integration infrastructure running in our own data center to AWS EC2 Mac. So the breakdown today I'll give a bit of background on what our team does at Block, a sort of existential crisis we found ourselves in a few years ago. We will do a bit of a closer look into the underlying hardware and infrastructure that drives the EC2 Mac product. I'll share details about what we actually built to make it all work. We definitely had challenges along the way, so we're going to talk about those, and we'll wrap up with a few takeaways, and hopefully have time for Q&A as well. So, Block, it's a financial service company. Most folks know of Block more from Square point of sale system, the family of products for small to medium businesses to take payments and manage their business, as well as Cash App, a peer-to-peer payments and investment platform. So mobile is a really crucial part of that, of those offerings. So I'm part of a team called iOS Developer Experience. One big aspect of what we do is we support the continuous integration or CI infrastructure that we'll be talking about. Our vast majority of our workloads are all from CI, from developers opening pull requests to GitHub to have their code changes assessed, built, tested, thrown into a merge queue, and eventually landing in a final release. So our team's charter, besides the infrastructure, also includes, on the Square point of sale side, really direct support with the developer community and the code base, the Bazel underpinnings that we use for a code base of this scale. And then besides Square, we work very closely with Cash App as well, who has a very significant usage of our infrastructure as well, and a number of other teams actually who build various public and internal developer tools. Essentially, if you need an iOS build and it needs to be code signed or it needs to be distributed internally for all the engineers in the company, that's a service that we offer. A third big part of what we've been building and supporting over the years is Bazel remote build infrastructure and caching. So the idea here is that one CI machine that performs a build, a number of the intermediate artifacts that happen during that build will actually get uploaded to a central cache. Other machines will then transparently pull down that work that was already done by a different machine, if it can be determined that it's identical, that it doesn't need to recompile it again. And developers actually pull this same cached data down directly to their laptops as well, actually going through CloudFront. Huge shout out to a lot of folks past and present on our team and neighboring teams. Jackie's here, was a big part of this as well, so Jackie will take all your questions at the end. So yeah, huge thanks to, this was definitely a big team effort. I will give a bit of the history tour, go back to 2014. I'll call Act 1 of Square's iOS CI infrastructure. So not maintained by a dedicated team. It was roughly 8 Apple Mac Pros running on vSphere. My understanding is that there were a lot of reliability issues, mainly due to the very different nature of those workloads compared to, say, a Jira server or a file server. A number of folks in this Slack thread that I resurrected were trying to decide if we should just buy a couple of bare metal machines instead. And that is definitely a beach ball that's sitting on top of a Mac Pro. If you get the joke, I'll give you some bonus points in Q&A. Act 2, we've very much outgrown that small little vSphere cluster. There is now bare metal Macs racked in a corporate data center. Our management technology consisted of power distribution units that we could remotely cut power and rely on the Mac to reawake when the power comes back, in cases when we lock ourselves out of the machine or SSH, et cetera. We'd have these Arduino-powered keyboard emulators, which give us the way to remotely restart the Mac into recovery, and then we would use that to initiate reinstallations, upgrades, even repartitioning the hard drives completely blind, which is about as scary as it sounds. And we had a couple of folks who were local to the colo, and they could come in and occasionally do remote hands, inventory, troubleshooting, et cetera. Act 3, we're now in a production data center shared with other block infrastructure, about 500 Mac Minis. These are the last 2018 Intel models. And so if you're looking at the timing and your sort of your Apple history, I'd say this is obviously when Apple silicon hardware was first released by Apple. Actually was released about maybe a month before these racks, well, essentially while they were in shipping to the data center. I'll come back to the story a bit later, but usually this is the part where I have to explain what do you need 500 Macs for to compile and build some iOS apps. So to give a sense of scale, there's 2 large code repos, 7.5 or so million lines of Swift and Objective-C, not counting all the dependencies. Several hundred iOS developers who actually contribute to Square and Cash App. And this is our current rough size in terms of CI machine footprint. To speak more specifically to the Square specific side, there's some more details in terms of how many hours of tests actually exist in the code base. Very large code base, it's hyper-modularized, so developers can work in isolation, but then there's thus a need to rebuild many different shared pieces of the code. And for both Square and Cash, the testing story has to be, it's extremely important because these products help people move real money. So everything has to be tested end to end, and testing is comprehensive. So there's a few graphs I can use also that I think illustrate some of the kind of performance at a certain scale challenges we have. And I'd say it's a pretty common problem in CI in general, and maybe more so with CI on Apple hardware, that just the compute resources are constrained. In a compute system where there's not much headroom, very small changes can have a big effect. This is an example from our Intel data center days, a 2-week period. Green is CPU temperatures. What's more important is the little dots on the side, on the upper part of the graph there. And every dot is a throttling event, where the CPU is throttled down from either 70 down to potentially as low as 50%. We actually saw some more extremes as well. The only thing that happened between the left-hand side and the right-hand side is that a code base upgraded its iOS simulator version for the majority of its tests. So creating a lot more throttling, huge impact because it means all the work that the CI machines do slows down. We run out of capacity, so job queue begins to grow. Developers are now waiting, looking at potentially half an hour extra amount of time to get a status check on their build. That's the thermals part of things, the disk IOPS aspect here. So this is disk IO read events over the entire cluster. This is a 4-day, those 2 rabbit ears peaks there are 4 business days where the cluster had Xcode 16 installed on the cluster. It was then removed for a little while we troubleshooted the issues, and this was due to a pretty important set of builds that normally would take 30 minutes growing to take 90 minutes or longer. So it's a bit of a different situation than the previous slide where a config change was made and tried, and then that can be rolled back. In this particular example, the users or the CI code had no changes, but this was just us making a change to the infrastructure. And what we thought would be sort of an innocuous change, but turns out it was not. And then finally, the need to cache a lot of large files and assets, and large files and many smaller files to optimize the performance of the simulator. So a single pull request run for the Square Mono repo, there can be hundreds of test suites easily that need to be run, which means a lot of iOS simulators. So this graph is a timing graph. The y-axis is 3 minutes, the range of the y-axis. It's the time that it takes our Bazel remote testing system to boot 3 iPad simulators in parallel and also prepare them for accepting a test workload. And so every one of these inflection points on the graph is a particular sort of investigation we did to try to optimize as much as possible. And so one benefit of this particular work is that we have a more efficient system because the simulators are spending less time just booting, but actually the more important latent effect of this work is that at every inflection point here, CPU, disk, memory, and network bandwidth all have a strong correlation with going down, which is in the right direction. So we work very hard to keep the test environment as lean as possible because we know that there's always this problem of resource contention, and that really impacts the reliability and the stability of tests. And with testing, flakiness is already its own problem. We really don't want to make it worse because of infrastructure issues. So those are a few examples of the sorts of scale problems that we run into. So coming back to that story now, we had those new racks delivered, Apple Silicon's out. The whole shape of how Mac compute really is looking is quite different now. We took this time to really evaluate, we've been doing this for, 7 or 8 years. We've been keeping up with all the platform changes, rebuilding our tools several times over, but this is actually like a really huge change, and this might be, an opportunity to step back and revisit. So to talk about some of the pain points, right, of what we had been running with our on-premises environment. So we made our whole setup work well enough, I would say. There was just a lot of high-touch, what we call toil, involved in maintaining it. We had configuration management, so we could have a relatively consistent, application of the machine config. But Xcode installations, simulator installations, there's a lot of time involved, but actually the worst, maybe one of the more problematic issues is that macOS also, when we would upgrade, it's a one-way upgrade. We can only revert it by getting remote hands on the machine and doing something that we can't do remotely. So that upgrade process would be done extremely carefully. It would take a long time. There would also be a category of build failures that I would classify as the cobwebs in the machine problem, which is we have these very, very like months-long OS installations, thousands of builds that have been run on them. They can get into a weird state that is not even really worth the time debugging, and so instead we'd refresh them, but make a note of the host name so that if it happens again, we take it out of service, and then deal with then the next steps of that. So not great. We also had no disaster recovery redundancy plan whatsoever for the hardware, and we were concerned that there could be a human error, something that could get the machines into a state where we're essentially locked out of them, or worse, like an actual data center incident. We just had no backup. So these are the USB keyboard dongles. They are great for us to help them manage the machines once they're up in a running state, but bootstrapping from zero was not possible without remote hands. We'd also written, in some cases, up to almost a petabyte to older models of our Macs that we were running, and we were starting to see signs of disk failure, and we're not going to be able to replace those in the field. Generally, our fleet was like one static set of all these single kind of hosts, but when we would start to want to have the flexibility to adopt new hardware, we really would have to be like, first of all, there'd be a lot of planning. We'd be looking at a year up front, annual budget, planning, CapEx sort of thing. And we'd be always in this question of should we wait 3 more months because there's all these rumors about the next Mac Mini, will we deliver these and then wish we had waited, that sort of thing, buyer's remorse. Apple then goes and releases the M4 Mac Mini. We want to be able to use that as soon as possible and have the flexibility. We don't have that with the on-prem setup. And I also would always use the term, I would say that we live in a weird island on the network. So we would generally, our way to access other services at Block would be done in sort of an exceptional way. So we couldn't really take advantage of a lot of the most common platform infrastructure type tooling and systems that had been built at the company. Things were exceptional through firewall rules. And as more and more of the engineering was moving to the infrastructure to AWS, our integration points were starting to disappear, and that was making life hard. To talk about some of the things that made Amazon EC2 Mac look very appealing to us, a big one is the bare metal snapshot capability, being able to take a block level snapshot of a physical Apple Mac hardware and instantly, or near instantly, boot hundreds of machines off of that same snapshot, all below the level of a virtual machine, right, directly on the hardware. We can also then have the flexibility to roll back an OS upgrade. There wouldn't even be a concept of an OS upgrade. It's just run this AMI on this machine. That sounded really great. We wanted to completely get rid of that whole inventory management toil aspect I was describing, and also flexibility to use some additional capacity when we need to do upgrades or testing without having a whole conversation of what percentage of our production fleet can we afford to cordon off to go and test this upgrade. So get rid of all the administrivia related to that. We wanted that flexibility to adopt the new hardware that comes out as it comes out. When we need, if we want to be able to change a portion of our cluster to a different instance type that makes more sense, like everyone else gets to do with Linux type instances, for example, we want that ability as well. And then the big one, of course, right, is integration with the rest of AWS. So the idea that we could assign an IAM role, an instance profile to an instance and authenticate to other services, running in other VPCs potentially, use secrets manager, trigger lambdas, things that other parts of the company's CI systems actually were already cut out to do. This would actually enable us to use those exact same services and be more of on an equal footing in terms of CI systems at the company instead of being the weird island. So it's been helpful for me as someone who's interested in systems in knowing more about what's really going on in terms of the implementation, because we've been able to use that knowledge to make certain decisions and to help troubleshoot. So I'm going to just share what I think sort of are the important takeaways there. So this is an image that lots of folks have probably seen. It's a public photo. You can find, there's the link on GitHub to find it. It really shows in one image what's been built to make this all possible. So up top we've got the Mac Mini as it comes from Apple. On the bottom is all of the custom silicon that comprises the AWS Nitro system that Manish was already talking about. This allows the offload of all of the networking, storage, all the instance management, access into understanding of VPCs, security groups, all that stuff. Zooming in, we see also all that extra connectivity, all the external connectivity that enables the extra storage, networking. That's all done through Thunderbolt here. There's connectivity for manipulating for USB devices. There's a real video device on HDMI. And then what's happens to be cropped out of this photo is the part where you need to press the power button, which is the only supported way to enter the recovery environment on an Apple Silicon machine. That's all automated. So it's a reminder to me, this photo, that as amazing as Apple's hardware is for a desktop use case or a laptop, it's not a server device. There's no KVM, there's no out-of-band management, there's no Pixie boot, right? Everything is done through manual actions in the recovery environment. And this is kind of a core part of the security design of Apple's platform. Makes a lot of sense for an end user, makes it more difficult to run it like it's a server. So had we continued to go down this path of running our own infrastructure, there'd be a lot of engineering that we would actually have to do as a team. And then again, the M4 Mac Mini comes out and the dimensions are in a different shape and the power button's under it. We would be on the hook to have to figure out the solution, right? So now someone else is. So it was really about our team deciding on what was the most important thing to focus on our core competency, any time we're spending not working, or we're working on something like this, we're not serving our customers in a direct way. And if you're like me and we're more curious about what's going on, how the machine actually boots, so this is the disk utility app. This is what you'll see if you look in an instance. There's the SSD from the Apple internal SSD is still there. It's gray there because it's unmounted. You can mount it yourself if you like. There's a volume there that we've created. I'll hand wave over that for now. But the point of this is that we are booting from an external Thunderbolt device to the Mac. This is just an external Thunderbolt device. It's powered by EBS and a block store. So this is exposed as an NVMe device through the Nitro system. And under the hood, when it comes to the orchestration of all of this, essentially the automation behind EC2 has to be involved to put the machine into recovery, know how to select the boot volume, all the stuff that a human would have to normally automate, they would have to type out or use the mouse themselves. So all that's being done behind the scenes. All the Mac knows is it's got an external NVMe Thunderbolt device. And when that boots, the EBS system will be connected back to some snapshot-backed AMI that it's booting from, and it begins to just hydrate through EBS in the same way that any other Linux or Windows instance would. That's the closer look at the hardware. We'll talk about what we built. This was also all built in parallel to us full-time supporting our current on-premises infrastructure. So we actually really took our time with this. We did have a mandate to get out of a data center by a certain date, but we had wiggle room. So this is the high-level networking environment diagram to show where the machines live. So they used to live in the production data center. There are still some on-premises services that are there that we now connect to from a shared infrastructure VPC. The Macs live in auto-scaling groups They boot off an AMI that we create. There's a user data that applies a last mile sort of configuration to those, and then they connect to a hosted Jenkins instance that we also run. Access used to work through IP firewalls, network ACLs. Now this access goes through instance profiles. What I like about this slide is that I actually think it's boring, right? There's nothing really Mac specific here. You can show this to someone and they can understand. How, if they're familiar with AWS, how it's like what it's doing, and it's also accessible to other engineers in the company in a way that the Mac instance our on-premises system previously wasn't. We used autoscaling groups as essentially our configuration primitive for these machines. So all of these things highlighted here are different dimensions, I'd say, of configuration. So Xcode, macOS, these are all predictable. There's a cadence to this. We upgrade these over time. We phase new things in, phase out older versions. They're predictable. Other things are more ad hoc, right? So we know that we need different environments to run in, but there may also be new instance types that we want to experiment with. We want the ability to run our own separate beta versions that are isolated from the rest of the cluster, for example, to eliminate that problem I showed earlier with the IOPS spike. We do try to make one very large configuration that supports the majority of workloads because this helps accommodate the very spiky nature of CI workloads. But what we love is to not have any friction to setting up alternate configurations that are much smaller in size. So that's where the autoscaling groups come in. Because we're using Terraform to manage all the AWS infrastructure, there's an abstraction on top of autoscaling groups and their launch templates in a Terraform module. And this is literally the extent of the configuration for our sort of production group. We have the knobs for changing all the things that we care about changing. And when we want another group, we copy and paste that group to something with a different name, and we change some of the variables. And we'll have different Terraform vars files for different development, staging, and production. We can show this as an example to somebody who wants to run an experiment, and it's pretty self-explanatory what's going on. They can open a pull request, we review it, it merges, it gets deployed, we wait a while, and then we have our new like sort of isolated experimental group, right? Or we can do this to do kind of gradual shifts of upgrades, for example, balancing out different size ASGs. This setup also was like, as an example, this is an example of Xcode 16 beta testing that I was doing. So this allowed us to roll out every single Xcode 16 beta over the course of the summer and make it available like in a small capacity in CI, and code owners could actually go and make code changes to get compilation working again as Apple would change the Swift compiler rules, for example. We're talking about making customizations really easy and low friction, so we applied the same philosophy to how we'd build AMIs. We had already Ansible as a configuration management tool for the on-premises setup. We took that repo and added a CI pipeline to run the exact same, or nearly exact same configuration to machines that were booted and run through Packer. So Packer will spit out an AMI at the end. I have to mention, of course, so EC2 Image Builder now supports running on macOS as of, I think, the last couple of months. So that's also an option. We also use Packer to build more than just AMIs, so it actually still makes sense for us as an abstraction. But this is just an example of what the pipeline will do. We'll build and do some additional post-processing. And we'll also actually add some extra tags to those images that are built, and that kind of acts as just a simple inventory. We can trace an AMI back to the original CI pipeline that built it, for example. A big advantage that we found in doing it this way, so the automation really gave us a kind of new capability in that because we run this build so often, we run it daily to make sure that it's always working. We're not in a situation where like a large number of things in the configuration drift have kind of broken and then we have to fix things all at once. Because we build them so regularly, the delta of changes in them is very small. Because of that, deployments of these changes are super low risk, and because of that, we deploy them a lot more often. We don't end up so much with really old, these like long-running installations that, we may have made some, might have been some human error involved in like certain machines getting into a wrong state, right? We have this kind of continuous provisioning system that's always being exercised. So in this new world that we're in, where we don't have long-running installations, we don't actually have instances running for more than a few days, which is great. Things are actually a lot more stable. The environment's more consistent. We've got a new problem of, we need to make sure that a terminated instance is not going to break somebody's job. And the pretty clear solution here looked to be auto-scaling group lifecycle hooks. And taking the strategy of us not really trying to reinvent the wheel, looking for something that wouldn't take us very long, we looked to what was available. We found an open source project by BuildKite called lifecycled. It's a single binary that you run on your instance. What I love about this solution is we only wrote code to create these few AWS resources in Terraform, and then we wrote the code that actually knows how to talk to our Jenkins instance and drain any running workloads on that machine. And what ends up happening is that machine will get a notification saying, you're about to be terminated, and it says, hold on, I'm going to go finish what I'm doing. When it's done, it comes back, and the machine can be safely terminated. This particular thing, it wasn't very complicated to implement, but it was a really important milestone in what we were building because we can now make changes any time of the day, and we could exercise those deployment workflows within the team. So I showed earlier the boring diagram. This is the more interesting diagram. This was also a system, I'll caveat, that was built as a separate parallel project from this whole EC2 migration. So this was net new, kind of just built at the same time. On the left hand is that set of CI machines that we've been talking about up to now. On the right-hand side is another cluster of EC2 Mac instances, which are only there to run iOS simulators. Because if you remember, I said there's 28 hours worth of tests in the code base. So these tests run in a very optimized environment that's actually inside a macOS virtual machine on Apple Silicon. The VM's really optimized to start up fast, and all the things that needed to be cached into the environment for the iOS simulators is already done. And call back that boot time graph that we saw earlier. So right now we're running 3 of these on a single Mac2-M2 in parallel. I think now, given this optimization work we've done, we can increase that further. These are also all run directly on the Apple SSD instead of EBS. We'll get back to that a bit later too. The underneath the AWS infrastructure part of this, right, is again a lot of pretty standard components. If I look from left to right, the flow looks like we've got the build machine, which uses Bazel. Bazel uses gRPC to do the whole remote build protocol. We use private link and VPC endpoints to get from one private VPC to another private VPC because there's a lot of bandwidth involved in this. That hits a network load balancer because that's a native target of private link. It goes through an application load balancer because that lets us do layer 7 health checks, and it understands gRPC. That traffic goes into one of the pieces of an open source project that's called Build Farm. So that's what we've implemented. You can run a scheduler, and you run these different what are called worker nodes, essentially. We use storage-optimized Linux instances in ECS for the storage component. Elasticache Redis is used as a coordination point. And then those Mac-optimized simulator VMs that I mentioned are off there to the side, executing the tests. Again, the same theme of let's use existing solutions as much as we can, and we can leverage more available expertise and proven patterns for all of this networking and compute infrastructure stuff. And our team can then focus on the part that we know is really important, which is the details, nitty-gritty details of the Apple sort of environment and build tools. Let's talk about some of the challenges. EBS, we would find when we were first getting started, we would run some workloads on the machine, and we would see things that would normally take they should just take a few seconds, would take a few minutes. We'd have a case where a build that's running, we might have a case of like a network interruption on the machine. And sometimes we would go and investigate an issue further, and we would see things like a process that's stuck, or we might even see that the machine's not really responding well. This could be especially driven from like large operations with Git, or if there was like swapping happening, for example. So what we learned, and this is fairly, I think, well, seems like common knowledge maybe for folks more experienced with EBS, which was not us. But the understanding that when a volume is a snapshot-backed volume, well, that snapshot has to come down from somewhere. It comes actually from S3 in the back end. And all those blocks on the device have to get into that NVMe device that's connected to the Mac. That's both reads and your first writes also still have to pull that block for the first write. And so there's actually a documented solution from AWS on how to do this. Mac, all the benefits of the abstraction there also, I think, kind of work against us in this sense because the NVMe device the Mac doesn't know that it's backed by a network, block storage system. And there's a lot of I/O going on macOS. There's a lot of auxiliary services that are running there in the background, and then we add Xcode and other things on top. There's a lot of I/O. The monitoring that we had in place actually helped us understand this a little better. So we have CloudWatch metrics on the top here, and then machine stats metrics on the bottom. And we can see where there's that flat line in yellow in the upper right. That's the point where the Mac is recently booted, and we can just see from the metrics like how much work EBS is doing to just get those blocks hydrated while the machine is booting up, and like all the background daemons are warming up to do their thing. And then we can see once that queue starts to recover, you see below it on the bottom right that curve of what the macOS kernel is actually able to report says like, hey, I've got a lot more I/O available now. I can go and I can catch up. We found that this view was really helpful to look into performance issues because we really have the view from the storage controller side, but completely abstracted from the operating system. And then we've got the part that's reported by the macOS kernel, which is where your builds are actually running, right? So you can see what's the cause of the issue, or you can make correlations in this way. So some recommendations. This is directly pretty much from Amazon's documentation. You can warm up the volume by forcing to read the entire raw device, and that's going to fetch all the blocks and hydrate the device so that way your next I/O operations on it you'll get the rated speed that you're paying for on the volume. I'd recommend to not do benchmarks in isolation, but actually run them on real workloads because one of the big issues that helped us see this was the network interruptions, for example. So it's important to test these for real and not just look at your I/O speed of your EBS volume. Try to avoid exceeding memory because the cost of swapping onto EBS there's a performance impact there from our experience. You can also consider a brand new non-snapshot backed volume to do the majority of your reads and writes activity, so that won't incur that first read penalty. And you can also consider trying the internal SSD, because honestly, those SSDs they're pretty great, they're fast. I'll caveat that AWS does not officially support this. The SSD has to be in the machine in order for it to boot, so it's there, but they stipulate, it's free to use. There's obviously no durability, but it's a thing that you can potentially do if it makes sense for your workloads and you can get the performance improvements. Oh, and do your own testing with real-world workloads to figure out what's the sweet spot in terms of IOPS and bandwidth settings. Another challenge that we had is that our Packer build AMI is layered. We do 2 passes of this, and we would run into this situation where we would boot the final, our final launched instance, and our networking health checks would fail, and we couldn't access the instances. And because we don't have an actual keyboard attached, I can't ask someone in a data center to go and crash cart this machine for me. We've got to do our own forensics, which is actually quite easy to do just using a few click ops in the console or API calls. So we would shut down the instance that doesn't seem to be working properly. We can snapshot it as a backup. We attach that volume to another instance, and we can mount it and look at the logs. I found that the var log Amazon directory was really insightful, because you'd get all the debug logs from the sort of wrapper script used by the networking driver. And there's also EC2 macOS and it logs in there, which can give some insight. What we determined was the problem is that because this network interface is, well, on a system, the ways that an interface might get enumerated is not totally deterministic. So what it seemed like was going on is that when we would capture an AMI, the Thunderbolt device might be EN4, might be EN7. We would be saving that into our AMI and then trying to boot on another instance. And the clue here was basically from that ENI driver log, which was that it's expecting the identifier for the network interface to be something other than what's saved in the image. And so one solution, the first thing we went to do was delete a cache file that macOS uses to record the network interfaces that it has, and it's a sort of a stateful, file that gets updated regularly by the system. Actually, a more interesting discovery that we realized is that because this is a bare metal Mac host, when it gets a power off, or when it gets a stop instances command, there's no really, there's not a way that the OS automatically shuts itself down when it gets that signal, which is different than how a standard PC operating system or server operating system works. And so what this means is that a stop instances command is essentially you pull the power. You press the button down for 4 seconds and it shuts down. And what we realize is that our Packer build is just calling stop instances, and so we're doing the equivalent of just pulling a power plug, taking a block level snapshot of that, which is bad. So we simply added our own shutdown. This is 2 lines of fixes here. We would shut it down, wait a while, and then take our snapshot, and the problem was solved. So that's also just a guidance of if you're ever taking a snapshot manually, shut down the instance inside the OS first before you take a snapshot. AWS has given us imaging superpowers, and so we have to know what we're doing with them. We also lastly ran into a challenge of limited host capacity. We, at the point where we needed to begin scaling up more, we didn't really have the capacity we had expected to find in the one region that we could be in. We were able to circle back and expand to more availability zones. And to be fair, our reps that we worked with were always asking us, when are you scaling up, by how much and when? And we honestly just weren't really too sure. And we didn't really anticipate this as being an issue. And so we weren't very clear on that for ourselves. So I would say that if you're expecting to kind of do a scale up or a larger deployment, and like your reps will ask you this, but plan out how much you're going to need and where. Be mindful of what instances are available and which AZs are available to you in the region. So if you can operate in more AZs than you were originally planning to, do it just for the additional availability of the instances. And you can also find out from reps what the realistic capacity is looking like. That's the speed run tour of our migration project. Last month, we packed up 500 Mac Minis and shipped them off to get refurbished. I'll do sort of a coda on what I think helped us be successful with this project. We actually didn't change anything related to the structure of our CI. I think it's a lot easier to migrate a system that you already know rather than, and resist the temptation to, well, while I'm in here, I might as well go and fix all this other stuff. It's actually, I think, better to usually migrate something that you understand and change as little as possible. We're actually learning Terraform and EC2 as we were going along, and so we made sure that we followed as much as possible our own sort of dev to stage to prod workflow in building this out. It was really important for us to know that we could deploy something safely and mess up an environment as we're just learning how Terraform works, for example, or auto-scaling groups. The automated AMI creation that I already mentioned, made the whole development of the migration much. There was less manual involvement in having to create images. And we actually had a side benefit of it being very easy to support Intel workloads, that we could simplify their migration by saying, well, we don't need to migrate to Apple Silicon and your dependencies at the same time. We can just put you on Intel until you can find the time to upgrade your build tools. We actually also drove the migration of which project, like the sequencing of which projects to migrate and when. So we worked directly with project owners. It wasn't it wasn't a self-serve migration. We had maybe 60 or 70 different repos to move over. So folks who were interested in doing it early, they could adopt the faster Apple Silicon builds, and then they could give us feedback. And we also would use these we would use these migrations as milestones to inform whatever was the next thing we needed to build to support the next biggest repo that we were going to move over. And it forced us to be in the production mindset early on, and that we're actually running stuff. So now, we actually now need to, we actually can't destroy prod now. We actually need to keep it running because there's real workloads running on it. And that was also just motivating. And monitoring metrics, as you probably got from at this point, it's very important. Also was just really fun to be able to see how much faster a project will be building on Apple Silicon after we transitioned it from Intel. The bigger reflection, I think, from my reflection on us having conducted this whole migration, was understanding more about what we were after and what we were good at, but also in understanding what we were not interested in actually building, and trying to really stay focused on where we're kind of, delivering the best value. And what we realized is what we're interested in is a platform on which we can build this Mac CI kind of hardware and network infrastructure. There's commonly questions we'll field internally of folks asking should we outsource our UI tests or our CI machines to an external vendor so that we can solve in the hopes that we'll solve some of these problems. But at our scale, that typically one is very cost prohibitive, but it also cuts us out from a lower level of access to the hardware where we can optimize things much further and do something that's very specific to the needs of our customers. So I think the takeaway here is we realize that we need to have a pretty deep understanding of the technical, the hardware and the Mac platform and all these performance aspects that I've been talking about. we need to have access to that, and we want an understanding of it. We just don't want to physically manage the hosts, because there's a lot we want to be able to automate on top of it and integrate into all the other sort of cloud infrastructure patterns that are possible. And then to just use this capability to continue building out this infrastructure further. And that's the reflection, and that's the end. I really appreciate your time, and please fill out the survey.